All right, so now what we want to do is we want to start to use electronegativity values to actually classify bonds. So one of the things we do want to point out is that we are going to assign bonds as either being nonpolar covalent, polar covalent, or ionic. But just because you have a polar bond or a nonpolar bond doesn't mean the whole molecule itself is polar or nonpolar. You have to look at all of the bonds in the molecules and start to consider dipoles. But that will be a lesson for later on. But just make sure that you do differentiate between there being a polar bond and there being a polar molecule when that time does come. So what we're going to do to classify bonds using the electronegativity table is we're going to find the difference between the two atoms. So if we were to consider carbon and bromine, okay, so carbon and bromine. So carbon has an electronegativity value of 2.5. So we would take 2.5 minus the electronegativity value of bromine, which is 2.8, and that would give us a difference of 0.3. So since the difference in those electronegativities is 0.3, we would classify that bond as a nonpolar covalent. Keep in mind this scale is just really rough guidelines. We're going to see some examples where we have to start to use some chemical intuition to assign whether a bond is actually polar covalent or ionic. So an example of a polar covalent bond would be carbon and oxygen. So carbon has an electronegativity value of 2.5 and oxygen has an electronegativity value of 3.5. So the difference in the electronegativity is equal to 1. So we would be able to assign the carbon-oxygen bond as a polar covalent bond. We would also, let's look at an ionic bond. If we were to look at sodium and fluorine. So sodium has an electronegativity value of 0.9. Fluorine has an electronegativity value of 4.0. So we take the absolute value, and that difference gives us 3.1. Okay, so this 3.1 difference in the electronegativity values would allow us to classify that sodium fluoride interaction as being ionic. Okay, but let's consider another example. So we have hydrogen and fluorine. So hydrogen and fluorine, if we were to look at the difference in those electronegativity values, hydrogen's 2.1, fluorine is 4.0. Whenever we find that difference there, the difference is 1.9. So going solely off of this table, we would classify this as an ionic bond. But what we need to do is we need to think back as to how we classified things as either being covalent or a molecular compound or ionic. So remember that we classified covalent or molecular compounds as consisting of two or more nonmetals. And then for ionic compounds, we had a metal plus a nonmetal, or if we had a polyatomic ion, it might have been more than one nonmetal. Okay, but if we look at hydrogen fluoride, so hydrogen's a nonmetal and so is fluorine. So if we're using electronegativities, we would classify this as an ionic bond, but using our chemical intuition, we would classify this as a very polar covalent bond. So keep in mind that as we're looking at this, you need to think about your metalloids and things, but really like this section right here on the periodic table, those are going to be your nonmetals that we're considering. So if you have a nonmetal with a metal, those tend to form ionic compounds. They may be weaker or stronger depending on where they're at on the periodic table, but we really just want to use this as a guideline because there's really no such thing as a purely ionic or purely covalent compound. But we're going to kind of paint with a broad brush, and we're going to say that if it's two nonmetals and then the electronegativities are probably, the difference in the electronegativities is less than 2, then we would call that some form of covalent bond. We just have to find the difference to determine whether it was polar or nonpolar. But you need to start to use some chemical intuition and combine that with that electronegativity chart. So go ahead and commit these values to memory. So your 0 to 0.4 is nonpolar covalent, 0.4 to 1.8 is polar covalent, and greater than 1.8 is ionic. And typically, we'll have enough information if we have something that falls right on one of the transitions, like 1.8. We'll have enough information to classify it as either being polar covalent or ionic from our experience. So as we look at this, let's really differentiate between covalent, ionic, and metallic in terms of electrons now, instead of just talking about it being a metal or a nonmetal. So for covalent bonds, there's actually going to be sharing of electrons, okay? So if you had a molecule of hydrogen, and each one brings an electron, they're going to form a bond. And what we're going to say is a bond consists of a pair of electrons. So one pair of electrons, if they're being shared, is a chemical bond. And right now we'll go ahead and specify that as a single bond. Okay, but then for an ionic compound, we talk about sodium chloride, so we have a sodium ion and a chloride ion. The electrons have physically been separated, okay, so sodium gave up an electron, so it lost the electron, and chlorine gained that electron. So there's an electrostatic force, so there's a positively charged species interacting with a negatively charged species. So the electrons are not being shared there. And finally, the last type of compound that we want to introduce is a metallic compound. So if we want to think about a metallic compound, I'm going to try to use some squares here to represent the nucleus of different metal atoms. So here we have a whole bunch of metal nuclei. What we'll see is those available valence electrons are able to move freely, while those nuclei are more or less set. And that will give the metals some different properties, but depending on how many electrons there are and some other different things, that will give you the properties of the metal itself. So some of the properties that we want to look at for ionic compounds is ionic compounds. So remember we said that the greater the difference in electronegativity, the stronger the bond is. Well, ionic compounds have extremely large differences in electronegativity. So they have extremely strong interactions. So if you have a really strong interaction, your melting points are going to be really high. So whenever we want to think about ionic properties, think about salt. Okay, so whenever we set salt out on the ground, it doesn't just start to boil or anything, okay? It doesn't melt. So we're going to think about ionic compounds as having really high melting points. They can conduct electricity in the molten state. So that's whenever they turn into a liquid. They're soluble in water, so they'll dissolve in water. You can recrystallize them. Some of them, like whenever we're looking at something being dissolved in water, they can still transport electrons, so they can still conduct electricity. Compared to covalent compounds, which consist of nonmetals, they have low melting points. Okay, so an example of this might be a crayon or something. If you put crayon on a fire, it will melt, whereas if you put salt, it probably will not. But covalent compounds do not conduct electricity, and they tend to be brittle. So like waxes are extremely brittle. You can snap wax quite readily.